Hi. So I'm trying to derive equations for using back propagation to uh, optimally calculate the coefficients for linear regression models. So let's start with what the equation for. So first thing we have to start is simple linear regression, wherein number of features equals to 1. We'll take only one feature as input to the model. So therefore uh, x would look like um, it would have n examples, n samples, and only one column. Y would look like n, and it would have n samples and only one column. Therefore, because there is only one column in x, we need weights that would be a scalar, that would just be a number, that would be uh, getting multiplied with this one feature, the value of one feature, and bias is also obviously a scalar. Therefore, let's derive the equation. So let's say y hat is the value that the model will predict. We'll say y hat equals to w x plus b. So here wx will give you, this is a w is a vector of n length for n samples, and x is, sorry, pardon me, w is a scalar, and x is a vector of length n. Was let me note down that n is a number of samples here. Alright, so when these two multiply, they will result in broadcasting. So this scalar number, it will multiply with each of these, so it would become a vector of length n plus a scalar, so plus b. So this will give you a vector of length n. So y hat shape will come out to be same as y. I'll just erase these lines here because they were just for understanding. Okay, so now let's say if we want to, what we want to do is we need dw and db. So because these are the parameters of our models, we need to update these two things, right? These are the parameters, we need to update these parameters, so we need gradients for them. And these means, sorry, these are nothing but derivative of loss with respect to w and derivative of loss with respect to b, bias. So first we'll have to calculate the loss. So for linear regression, the loss is nothing but mean squared error loss, which is also equals to y hat minus y is error. We square them and we take the mean of it. 1 by n is the number of samples, So I, yi, and so this will be the loss. Mean squared error, this is the error. Okay, so let's break it into individual elements. This would be 1 by n y1 hat minus y1 plus y2 hat minus y2 plus so on. This is what summation will open up to. Therefore now so the loss equation is square of these, all the sums of squared errors, and then taking mean of it. So therefore d of, now let's move on to calculate dw. So dw is nothing but d loss of dw, which is, so we take this entire expression and we replace it in this equation of d loss by dw. Now so 1 over n we can just take out. This entire thing will become d over dw y1 hat minus y1 square plus d over dw y2 hat minus y2 square, so on. Simplify this expression. D over dw of wx1 plus b minus y1 square plus d over dw of wx2 plus b minus y2 square, so on. Again let's further simplify. So let's say we want to calculate the derivative of this expression with respect to w. Now this would be by the rules of derivations, this will become 2 times wx1 plus b minus y1 into derivation of this thing with respect to w is x1 plus 2 times wx2 plus b minus y2 times x2 plus so on. Therefore if we generalize this different pieces, now this is a term, this is a term, and all these n examples are summed up together. So this would become as 1 over n sum of, this we can call y hat I minus yi into xi, or rather let me see, xi. So sum of these two products of these two things, sorry, and 2 should be taken out, so this should become 2 now. Therefore programmatically we will write as dw equals to 2 over n into np dot sum y hat minus y vectorized subtraction, element wise subtraction, into x. So this will do element wise subtraction, this will multiply each example x with the error y hat minus y, and we'll take sum of all this together. I think so, that would be correct. And if you want to calculate if you want to calculate dB equals to d loss by dB, so I'm just going to take it forward from this point, so we can write it as 1 by n d over dB wx1 plus b minus y1 square plus d over dB wx2 plus b minus y2 square plus so on equals to 1 over n 2 times wx1 plus b minus y1, and derivative of b with respect to b is 1, plus 2 times wx2 plus b minus y2 times 1, so on. So this will become 2 by n summation of y hat minus y I into 1. So programmatically what we can write is 2 over n np dot sum of y hat minus y. Alright, so this would be the programmatically way of calculating gradient for backprop for loss with respect to weights and biases. Now okay, so if you see here in this in the simple linear regression formula here, this point where we are calculating gradients, this is nothing but the same thing that we just derived, 2 over an np dot sum error, which is y predicted minus y times x. So that is all element wise multiplication and subtraction happening. So I hope it is clear, and we have mathematically derived the gradient calculation for the simple linear regression. Now the easy thing here was that we had only only scalar weight, so it was pretty easy to do the derivation. Now let's go ahead and do the derivation for weights when there are more than one features getting input into the linear regression model. Okay, so now next is how do we define gradients or backpropagation in the case of linear regression where we have more than one features coming in as input. So let's call it multiple linear regression, wherein the shape of x is n by m, whereas n is number of samples, m is number of features, y is n by 1. So for each sample we have one prediction value, one label, one output basically. Therefore for this m is there are m features, so x I would look like as, say you have x of the shape x1 1 x 1 2 x1 3, or let's say just x1 1 x1 2 x2 1 x2 2 x3 1 x3 2. So this is n equals to 3, m is equal to 2. This is an example of x. There are each row has, each sample has two features. So basically there are two features in the data set and there are three samples. So n equals to 2, m is equal to n equals to 3, m equals to 2. So I'm taking this example because with m equals to 2 it would be easier to derive, to reach to the calculation, to dwdb calculation. So in this case, if m is equal to 2, we define our w, or rather I should say w, capital W, is a vector of w1 w2. It would be a vector of two numbers, w1 and w2, right? Now the shape of this is 2 comma 1, or simply 2, and b bias would again be a scalar. So if we write the equation for y hat here, it would be x at the rate w plus b. So at the rate is matrix multiply, so here x shape you have n by 2, y w shape you have 2, so this would matrix multiply would give you shape n, a vector of length n, and when you add the b to it, this will do broadcasting and it will give you shape n. So finally you get a y hat of shape, a vector of length n, right? So now let me take out all this. Remember, we are assuming m is equal to 2, that's why. Now this is our y hat equation. So if we expand this, so this would expand to x11 x12, right? 1 2 x21 x22. This matrix multiply with w1 w2 plus b. So this will turn out to be x11 w1 plus x12 w2 plus b. This would be the first term. x21 w1 plus x22 w2, this is second feature, this is first, plus b, this would be the second term, and so on. So this would become a vector of length n, right? Now this is our y hat. So if you define loss now, loss is nothing but y hat minus y, let me rewrite it, 1 over n summation over all i's y hat I minus yi squared, mean squared error. Now so if we bring in the terms here, expand the summation, so this will become 1 over n. Now y hat to start with, let's go step by step. So this will be 1 over n y hat 1 minus y1 square plus y hat 2 minus y2 square plus so on. So this will become 1 over n. y1 hat is this first element in this vector, right? Now, so this would be 1 over n y1 x11 w1 plus x12 w2 plus b minus y1 square plus second term would be x21 w1 plus x22 w2 plus b minus y2 square, so on. So this would be our loss. Now when we want to calculate dw, now here we want to calculate two things, dw and db, right? So first let's go ahead with dw. Dw will be nothing but a vector dw1 dw2. Why so? Because w is a two vector of length 2, right? Here we see that w is a vector of length 2. So whatever changes, if you are doing minute changes into w1 and w2, this would be impacting y hat to some degree. Now we'll have to evaluate how w1 is evaluating y2 y hat and w2 is impacting y hat, basically when we change minutely or to some degree these w and w2s, right? So therefore dw will have a vector of same length as w, dw1 and dw2. Therefore this would be nothing but a vector d over dw1 of loss and d over dw2 of loss. This would be the vector. Now let's go one by one here. dw1 equals to d by dw1 of loss. Loss is nothing but this entire term here, right? So 1 over n comes outside, or let me rewrite it properly. 1 over n times d over dw1 x11 w1 plus x12 w2 plus b minus y1 square plus d over dw1 x21 w1 plus x22 w2 plus b minus y2 squared, and so on. Therefore the first term, if we simplify, this would be 2 times, I am writing this thing as y1 hat minus y1. So derivative of this entire thing with respect to w1 is nothing but all these terms will go to 0. Derivative of all these terms will go to 0. So it would be just left with x11 plus 2 times y2 hat minus y2 times x21, so on. So this is basically sample first, feature first. This is sample second, feature first. So basically, if you simplify this would be 2 over n summation of y hat I minus yi times x1i. So x1i is nothing but all the samples of first feature dw1. Now similarly dw2, if we calculate, so it would be nothing but d over dw2 on these places. So this will come out to be 1 over n 2 times y1 hat minus y1 times x12 plus 2 times y2 hat minus y2 times x22. Over n summation of y hat I minus yi times second feature, all the samples of second feature. So this is what we'll see. Therefore, so if you see dw, now let's change the color of my marker. dw1 is nothing but this, right? If we go ahead and simplify this would be 2 over n all the errors for each sample multiplied by first feature of that sample, and we see first feature was this thing, right? So we can say that this, if we transpose x and multiply this with errors, yes, so this thing can also be written as x1 dot transpose and matrix multiplied with y hat, basically the error. So x1 is nothing but this entire column, and if you transpose this will become a row vector. So the row vector 1 1 x 2 1 x3 1. So basically n samples of first feature. If you matrix multiply this with errors, which is nothing but y hat 1 minus y1, y hat 2 minus y2, so on. So this is 1 by n, this is n length vector. If you matrix multiply these, basically a dot product, so this will become a one number, output will be one number, so therefore this will be dw1. Obviously we'll need a scaling factor, therefore this can be written as 2 by n np dot of x1 and y hat minus y. Now similarly dw2 can be written as 2 over n np dot of x2 y hat minus y, because y hat minus y is common factor everywhere. So if we see, we are transposing this here, if we can combine, vectorize everything together, dw1 dw2, if we say 2 over n np dot x dot transpose y hat minus y, so this would be the same thing, because x dot transpose will become 2 by 3 matrix. This was 3 by 2 to begin with, this was 3 by 2 here. So when we are doing x dot transpose, we get a 2 by 3 matrix where each row is an entire feature, all the samples for entire one feature, and then this y hat minus y is nothing but 3 vector length for 3 samples. If you are doing dot product of these, you will get nothing but a vector of length 2, and this is what you desire out of D capital W is equal to this, right? A vector of length 2, or basically number of features. Now let's see let's go into the function class where we defined multivariate linear regression. So yeah, the dw is defined as 2 over n scaled with for np dot x transpose and error. So this will give you a shape, a vector of shape and features. So similarly, if you'll in the same line, if you'll calculate the derivatives of this loss function, our expanded loss function with respect to bias, so you'll get obviously errors multiplied by 1 for each of these biases. So this would, then you won't have any np dot or any matrix multiplication to be done to handle it, and it will just be a simple summation of all the errors. It will be a scalar. Okay, so here you have to understand yeah, right. You'll reach to the same point as we the db thing here is same as we did it in the simple linear regression. So yeah, I'll end this video here. These were the main things to be thought of when when writing these classes and calculating gradients. Otherwise, once you have figured out these gradients, it's more or less straightforward uh, to do all those other definitions or calculations. Thank you.